who began Thanks. Who began studying broadband UV X-ray emission from AGN during his master thesis at the University of Rome, Tor Vergata. Sorry about the bad pronunciation. And further developed his temporal and spectroscopic analysis techniques during his PhD at Roma Tre University. After completing his PhD, Riccardo worked at the Institute for Planetology and Astrophysics in Grenoble and the Extragalactic Center for Astrophysics in Durham, in the UK. And since 2020, he has returned to Rome, expanding his research to include X-ray polarimetry. And in fact, he's been working on XP data. He's currently visiting the Harvard-Smithsonian Center for Astrophysics, where he's investigating the extended emission of a sample of quantum date sources. So please, Riccardo, take it away. Thank you.
Okay. Do you hear me?
There might be a
Yeah, the people online should hear you.
Blah, 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 blah.
No, it's not. No, it is.
Blah, 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 yeah. No. Okay. Good morning, everybody. I'm Riccardo Middei, and it's my pleasure to be here with you and talk about the origin of the soft X-ray access in type 1 AGN. And before I start giving this talk, I want to thank the organizers of this seminar for giving me the chance to be here. Thank you. And it's not working. Great.
Can you call it?
No, love that. It's okay. So just to give you a brief introduction of galactic nuclei, we know and we believe that in every galaxy in the universe, at their center, there is a supermassive black hole with a mass in the range of millions up to billions of solar masses. However, only in a fraction of this object, we have matter supply around the supermassive black hole, so that we have accretion onto this supermassive black hole. And in those cases, we are referring to them as active galactic nuclei in active galaxies. And I mean, this accretion process releases a tremendous amount of energy that is radiated, and the peak of this emission is around the optical and UV. And just to give you an idea, this emission comes from a very compact region in the center of galaxies. That's why the name. And compact, I mean, just to give you a brief idea of what compact means, just imagine to have something very small like a handful of grains of pepper, because they are black, and a big city like Rome. Well, this stuff here would emit and overshine the light produced by the old city of Rome. So we are dealing with something that is really extreme and empowered by matter of accretion. That is one of the most efficient methods in the universe to release energy. And actually, as I was saying, the accretion process mainly emit in the optical UV. However, AGNs are bright also in the X-rays, and actually we can observe them across the whole electromagnetic spectrum, from the radio up to the gamma rays. And this broadband emission tells already something about these extragalactic sources. First of all, we are possibly dealing with the thermal and non-thermal processes in action in this object. And moreover, this broadband emission, multi-component emission, is likely the result of the interplay of different structures and components. So we can say the IGN are likely composite systems in which, and we depict them as something like the central supermassive black hole, which is surrounded by an accretion disk of matter, and then a dusty torus, molecular torus, that can intercept and absorb the continuum emission from the cores. And we may have a relativistic jet of particles, or also cloudy regions orbiting around the supermassive black hole. And actually, what really matters when we study AGN is the line of sight and the viewing angle through which we observe them on the sky. So we may observe across different through different angles, from, for instance, looking through the jet, or mid angles or to the dusty torus. And these viewing angles heavily affect the spectral shape that we will observe. For instance, if we observe AGN edge-on through the molecular torus, for instance, we won't get enough stuff with some like XMM Newton satellites, but we can have beautiful images and a lot of information, for instance, from Chandra, which is an imaging satellite. Or in case we are observing down to the barrel of the gun, down to the jet of a realistic particle, well, in these other cases, we are not really dealing with the closest proximities of the supermassive black hole because the jet dominates the emission across the entire electromagnetic spectrum. However, as you can imagine, it is possible that we observing to some of these mid angles, not on the jet, not on the dusty torus. And then in those cases, we are a clear view, we may have a clear view, if there is not intervening absorption actually, of the closest proximities of the supermassive black hole. And I stress the fact that closest proximities of the supermassive black hole because we know that X-rays are produced there. So the analysis of X-rays is the best probe we have to understand the matter under extreme gravity regime. And why this? Because we actually think that the X-rays are the results of an inverse Compton process in which synth photons emerging from the accretion disk are, get energy, are kicked up to the CfA energies from this thermal plasma of electron, which lies somewhere above the accretion disk, on the accretion disk, and inverse Comptonizes the photons from the disk itself. Then either we get this emission that we call the primary continuum emission, that is the direct product of this inverse Compton mechanism, or we can see the effect of reflection on the surrounding matters. And in this case, when we have reflection in the spectra, we can see different signatures and features that are typical of this mechanism. And I would say that after decades of performing X-ray spectroscopy, we are quite proficient in understanding what's going on and figuring out what the different components in AGN spectra at X-rays are telling us. For instance, from the characterization of the primary continuum, the photon index and the energy cutoff, we have a direct, we can have, not really direct, but we can have clues about the physical properties of the hot plasma that produces the continuum, so its opacity and its temperature. Or for instance, analyzing the profile of the iron K alpha, which is a signature of reflection, we can say whether this fissure emerges from a region close to the supermassive black hole, or instead a distant one, so from cold matter. And I mean, we are quite proficient in that, apart from understanding maybe the missing piece of the puzzle here, the soft X-ray excess. So whenever you are handling a type 1 AGN spectrum in the X-rays, you won't have much problems in fitting the... fitting above 2 keV can be difficult, but not as difficult as understanding what the soft X-ray excess is. Because whenever you do, you will have in type 1 AGN something that exceeds and you cannot model with the primary continuum. So it's a different component that it's always there. And we know that the soft X-ray excess is there since days. And I mean, it's always there. And when I say always, that in every ensemble work that has been performed on type 1 AGN, the soft excess was there and was measured. Like the one I'm quoting here by Stefano Bianchi, the Gaisha sample back in 2009. There is also another one by Yotzi in 2020. And I mean, the soft excess, it's very difficult not to observe a soft excess in a type 1 AGN spectrum. And it's also interesting the fact that if we model the soft excess like a black body, so a pure phenomenological, if you want, also non-very sense model for this component, we see that its shape is not really feeling different black hole masses. So it's about, we are dealing with something that has a universal shape. And I mean, in light of this universal shape, we can say, okay, there is no dependence on the black hole mass. What about something we may expect? So if we assume, we can explain it with something we expect in AGN. So we can say, well, imagine we have a lamppost configuration of the thermal plasma and the accretion disk. So we have this thermal plasma that Comptonizes the seed photons above somewhere on the disk. and then this reflects on the disk. So if the disk is ionized enough, it will efficiently reflect the light from this. So under these, and then I mean, here we are close to the supermassive black hole, so whatever emission line is produced in this region will be blended and bumped by the relativistic effect. So this relativistic reflection framework may nicely explain, in principle, the soft X-rays, like an excess of current. And yes, it is not with surprise that this model has been tested on several X-ray spectra of type 1 AGN by the, for instance, there was on 34 type 1 AGN by Grammy, Krumi, 2006, or by Dominic Walton in 2013. And in both these cases, the relativistic reflection framework was successfully adopted to model the X-ray only spectra of these sources. However, this came at a cost. The cost of always getting quite extreme results in terms of the best fit parameters of the model. So in all these cases, for instance, if you want to fit the relativistic with the relativistic reflection, the soft X-ray excess, well, you will have a spin of the supermassive black hole, which is always close to be maximally rotating. And the same, you can work with the gravitational radii from which the reflection is observed. However, under this framework, we may expect, well, if the soft X-ray excess is a byproduct of the relativistic reflection, we should expect these two components to correlate. And actually, that was not found by Boisset 2016, in which there was an actual anti-correlation between the strength of the soft X-ray excess and the reflection fraction. So from this work, we were somehow expecting that and not finding that. Just like it may be the relativistic reflection and the reflection and the soft X-ray excess are not really the same stuff. And in light of this and previous works by some Polish group, we ended up with another model. So in this case, we are somehow dropping the idea of this lamppost geometry, but we are saying, what about an accretion disk that is radially stratified? So in this case, we have the stratification of the hot plasma, which is optically thin, geometrically thick, and then going further from the supermassive black hole, a warm plasma, which is optically thick and geometrically thin. So in this case, we can explain the computerization process of the hot corona, so the continuum one, saying that the disk is feeding this hot corona, and then we can explain the soft X-ray excess, saying, well, the disk photons from the disk are also feeding this tenuous atmosphere above the accretion disk, which is warm, and then we produce this soft X-ray excess. And actually, this idea was tested for the first time by Pop, Petrucci et al. 2013 on Markarian 509. 509. And actually, that worked. But as you can see, it's a sort of a real change of a paradigm, because we passed from a very famous and known geometry, the lamppost one, to something that is instead diskish. And in order to further test this and actually the reliability of this model, we really needed something that is not only X-rays, but we need UV data, you need soft X-rays and hard X-rays. Essentially, through the UV data, we can handle the soft, to the soft X-rays, we want to observe the soft X-rays data and then the soft X-rays. UV data, in our assumption of the disk feeding the soft X-ray excess and the hard corona, are super important because somehow they allow us to pinpoint the different components when handling and performing a spectral analysis. And then the hard X-ray data are important because through them we can constrain the reflection, the actual reflection component in the shape of, when shaping the spectra. And in light of this, we have been proposing several multi-wavelength, multi-epoch observational campaigns on different levels of AGN. So does this framework, the two corona model, works? Maybe yes, maybe not. The best way to test it is to have a broadband coverage, starting from the UV up to the hard X-rays. And then we ended up asking for XMM Newton and Nussstein. XMM Newton because of its large effective area, especially in the soft X-ray band, and then for the fact that UV observation came for free because of the optical model. And then Nussstein because we want to have hard X-rays there. And we have been asking that for several different kind of AGNs, starting from NGC 4593. And actually, that was the first monitoring campaign that we analyzed. And for each of these monitoring campaign, the idea of having multiple observation was very important because we wanted to test the correlation properties because of the different wavelength. For instance, as I said, if we assume that the warm corona and then the soft excess are somehow fed by the accretion disk, we want to see whether there is a correlation between the UV and the soft X-ray excess. And actually, in all the monitoring campaigns we have been studying, we always found, analyzing the different epochs separately, that the UV were correlated with the soft X-rays. We were not finding the same UV and reflection were not correlating. Reflection and soft X-rays were not correlating. And I mean, this monitoring campaign enabled us to test this correlation on long-time scales, like monthly one, the time you need to get all the observations according to our requested schedule, and also down to short-time scales. So within the observations, meaning the correlations on kiloseconds time scales. And then getting back to 4593, this was the first source that we studied and on which we applied this model. And at the time, the question was, can we really reproduce the spectra using this two corona model from UV up to the hard X-rays? And we found that it was possible to have very nice results using this model that came with quite naturally, actually. And I want just to point out that we didn't pick this object because it was the easiest one. Because in this source, in order to get like a complete spectral analysis, we had to add relativistic reflection that was there, distant reflection, and then contorization hard and contorization soft. So at that time, it was back on 2019, we were finding that it was possible to model the soft X-ray excess and the hard component using these two contorizations coronae. Maybe we were lucky, no? Just by chance. So we said, what about testing the two corona model on other rich data sets, starting from the UV up to the hard X-rays for different flavors of AGN? And actually, we found out that this two corona model was a viable explanation for the broadband emission spectrum from UV up to the hard X-rays. For instance, for the cases of 3C382 and HE11 something. And for those sources, we also found that the two corona models, so the one in which we have hot corona for the hard X-rays, warm corona for the soft X-ray excess, was performing better on a statistical ground than a pure relativistic reflection framework. And then we keep going with our campaigns, and here that's my favorite object, ISO511. Because this source was listed in the De La Calle sample. De La Calle sample contains AGN, type 1 AGN, is De La Calle 2010. It's called the Ferro sample, and contains AGN for which in the X-rays they have been observing a broad iron K alpha with high significance. Broad iron K alpha means likely relativistic reflection is in there. And then at that time, this object was observed back in 2007 and was known to have this broad iron K alpha and this strong soft excess. Then we got 5 observations in 2019, and the source was found to a very lower flux level, a factor of 10 lower, and the soft excess was gone. The soft excess was gone, and you can see here from this fractional variability spectrum that it's a way to say how many variability components you have in the spectra, and then back in 2007 we have something in the soft and something in the hard. Back in 2019, just a single component. So this source was somehow telling us that you may have a signature of relativistic reflection while the soft excess is not present. And then, and this I think has been on the, I mean, maybe it was on ARXIV last week, and then we performed our two corona model modeling on another kind of source that is RBS 3032. And this is an ultra soft narrow lensifter galaxy. So ultra soft narrow lensifter galaxies are quite extreme kinds of AGNs in which the disk is so hot and possibly so ionized that they peak, their peak is not in the optical UV, but in the far UV, the one of the accretion. And then if you think if the disk is very ionized, the reflection from the disk can be very efficient. So if you want me to say this, I can say that the idea of testing the two corona model in this source was somehow testing this model under the less favorable condition. However, also in this case, we found out that it was possible to use our model that was better performing than the pure relativistic reflection model. Moreover, at that time, times were ripe for a nice stuff that Xian and Valentine did in 3 years ago, that essentially the release of RX core, that is a model you can fit and expect that assumes two stuff. Assume a lamppost corona and then a one corona. And then say, okay, if I feed these two components with the seed photons from the accretion disk, what is the amount of energy released in one and in the other? And then by reproducing the shape of whatever soft excess I get, what are the different weights to the soft X-ray excess due to one quantization or to reflection? And well, in this case, we were just getting that the 95% of the soft X-ray excess we were getting here was likely due to inverse contact, not reflection involved. So in this case, after 6 years, 6 monitoring campaigns, we were getting a quite homogeneous scenario in which we were always finding the UV emission to correlate with the soft X-rays. We were not finding strong correlations between the reflected flux and the soft X-ray excess. We were also finding that the two corona model, either including or not including the relativistic reflection when needed or not needed, was fitting very nicely the spectra. Very nicely doesn't know me much, but in terms of statistic was very good. And in all these tests and tests we have done, a poor relativistic reflection model was really struggling in getting back a nice representation of the data. Even if we were having extreme parameters from these models, still the best fit was not there. And this leads me to my conclusions. After this spectral analysis that involved a lot of data, a lot of time and people, I think that we can say that the two corona model is a viable explanation for the broadband emission of type 1 AGN, meaning that the soft X-ray excess can be likely produced in terms of work quantization. And we have tested this at various Eddington fraction. But if you want, it's nice because we are saying that the model nicely works. The idea of using only relativistic reflection to account for the soft X-ray excess, to me, it's a bit old and not always giving us nice results, especially in terms of extreme parameters, like every time we get a maximally rotating black hole or we are just so close to the black hole when reflecting light, and it's quite extreme. Also, we get very high metallicities and stuff. And this is more a conclusion question. So instead of saying what's the origin of this component, we should ask ourselves what is the main process through which we have dissipation of energy. So are we dealing with something that is dominated by work quantization, that at this moment we can say there is work quantization there, or we should keep saying, oh no, it's that or it's the other model and try to fight? But I think that the best way at this point is just to say, okay, what is the most prominent how do you say, process through which we dissipate energy and then we release the light we observe with the soft X-rays. And also maybe we need to think and rethink a bit differently how the hot corona is located above the accretion disk. Because, for instance, In one case, the one of the realistic reflection, we have this lamppost geometry. However, this lamppost geometry is not really in agreement with the XP results on type 1 AGN, according to which we may expect a more discish structure of the hot thermal plasma that provides us the hard X-rays. And this slab-like, wedge-like shape is more in agreement with the two corona model. So maybe we have to rethink a bit and move to a new paradigm. And with this, I thank you for your attention.
Okay, any questions for Riccardo?
Okay.
Okay. All right. So what are the consequences, if any, from assuming that you're right?
Which is possibly wrong.
In that case, for the measurements of the black hole parameter from the airline stuff.
Well, so the point is that the iron line is something possibly related with the soft X-ray excess. So if we model, there is this nice plot, I think, that can be explaining my point. So if you see here, you have this big curvature of the spectrum down to 2K, this something like that, and this due to reflection. I'm not sure we have ever observed a broad iron curve now. I mean, with Prisma, we may have clues about that, but I don't think we will observe a broad red profile up to this point. So if we then get a nice modeling of the X-ray spectrum and maybe find something broad in this area, we may have different estimates. Maybe, but for sure, I mean, all these estimates, to me, are driven by the fact that we are modeling this curvature of the spectrum, but also the soft X-rays. And here is where we collect more photons. So this part of the fit is not driving the whole statistics of the fit itself. So are we estimating the spin parameters and all the parameters of the relativistic reflection from the profile of the line, or is that from the soft X-ray excess, which is featureless, for instance? So I hope we can have a better answer on this once we have also Prisma data and stuff. But for sure, I'm a bit skeptical about this kind of results because when you have such as, I mean, your fit is grasping that part of the data and say, okay, I won't move from here because here you have a lot of counts. So we will see with Prisma data, I guess.
Do you have any follow-up questions or?
Can you show your figure that I think you did show earlier of the geometry of the hard versus the hot versus soft corona versus the lamppost? I'd like to see if those, yeah. So the hot corona is the way you're showing it there, a enhanced ring around the black hole, correct? We're looking at it.
Yeah, possibly yes.
Okay, and the soft X-ray is coming from the disk.
From a thin layer above the disk.
Mhm, okay. Yeah, fine.
And then here, I mean, this is a model in which we assume that the accretion disk is completely passive. So all the energy is released in this warm upper layer above the disk, and you do not expect the disk to dissipate much energy. And you just have radiation from this layer. For instance, there are the models by Chris Don, in which they have three phases. You have just outer disk, warm corona, and hot corona, which is another way to see that. But you won't have this sandwich-like shape. You have three different components. Here we are somehow assuming that the disk is not playing a significant role in this close to the supermassive black hole regions.
Yes. Yeah.
What is the relation between the two coronas? can they exist independently? Namely, where is an AGN that only shows the soft excess and does not show a hard X-ray emission?
Okay, I think there was a paper by Claudio in which they were handling something very soft, but was not a soft X-ray, it was a disk emission.
The only AGN that I can think of that is in a purely thermal state is the source found from Ashma, published in 2012, but that seems to be a long-lived type of disruption event. So if the two coronas are in your picture, seems to be possible that they exist independently, then
Well,
one would find.
so
such AGN.
you always expect to have hard X-rays and then the hot corona. Because it's the power law we observe since we start observing the X-rays, right? From AGN type 1. Then, as I showed you in some previous slide, the soft X-ray excess, it's always there. So this two corona is just a way to model the UV up to the hard X-rays emission of these guys. And then if you use it, you have them at the same time. If you start further correlations, you see that the flux emitted just from the component you use from the warm corona nicely correlated with the one that you see from the hot corona, meaning that you are possible. I mean, part of the emission of the soft coronas is intercepted by the hot one, so from soft to hot. And this is again inverse contact, just feeding fed not by the disk, but the warm corona. So you expect them to be there both. For instance, in ISO 511, there was no soft excess and we only had hot corona. But that was a bit extreme because we found it in a very low accretion state. So if you find something, we shall discuss it.
I'm afraid we need to move on to the next
Okay.
speaker, but thank you so much, Riccardo. So, Paul might be discussing some ways in which we can use new star only to constrain black hole spin. Yeah, so I'll introduce Paul in the meantime. So, Paul is originally from Romania and he earned a bachelor's degree in physics from Stanford University in 2019. And this was followed by a PhD at the University of Michigan in 2024. During his time at Michigan, Paul worked with Professor John Miller on characterizing black hole rotation. He is currently an MIT Kavli Fellow, working on several topics regarding compact objects and high energy astrophysics in general. The aim of Paul's work is to expand our view of the formation and evolution of stellar mass black holes and their connection with their surrounding media. So Paul, take it away and thank you for accepting our invitation.
Yes, thank you. Can you hear me? I can hear myself in the room, so I assume that you can hear me as well. Thank you so much for being here. Thank you so much for the opportunity to speak in front of this audience. As I was just introduced and as you've probably seen in the email and the abstract I sent around, today I'll be talking about my work on trying to characterize the distribution of black hole spins in X-ray binaries. The distribution of spins in black holes in X-ray binaries. To give a brief outline of this, first, I like to always try to spend a bit of time on the background and motivation, though I hope that given the audience today, I will not have to convince you why this is important, but then I will quickly transition into some of the techniques that we can use to actually gain some information about black hole spins. I will transition into my work. And then just at the end, spend 1 or 2 minutes or so just talking about possible directions in which this project will be going. Now, I will be talking about my work. I will not be talking about the status of the field. And that's because I find my work more exciting. When we look at the spectrum of masses for compact objects, those go all the way from down there, less than a solar mass for white dwarfs, all the way up to the millions or billions of solar masses in the supermassive black holes that Riccardo was telling us about. However, my work focuses on that end of the spectrum, on stellar mass black holes. Those Those are the natural consequences of stellar evolution. The most massive stars will end up dying and turning into those stellar mass black holes, and those range in mass from somewhere around 3, 5. We'll see in the next slide why that is uncertain, all the way up to hundreds of solar masses. Now, this figure over here shows on the y-axis the mass of the compact object that is formed from a progenitor star, or a different mass shown on the x-axis. And the curve that I want you to focus on is the red one over here. Now, at low masses, below couple solar masses, we understand the physics of what happens when a star dies fairly well. We know that low mass stars produce white dwarfs. However, this picture becomes much more complicated when we look at higher masses. When we look at the stars that end up forming neutron stars, and even further up at the stars that form black holes. And you see over here a lot of dashed lines, kind of indicating that we're not quite sure what's happening there and what masses are being produced from the most massive stars. How do those black holes, or maybe even neutron stars, look like? And a great way to look at the black holes that end up being formed is to, well, actually look at their masses. This figure is a figure that is now a must in every talk about stellar mass black holes. This shows the distribution of masses of compact objects of both neutron stars and black holes that we're seeing through electromagnetic radiation and gravitational waves. I will focus on the black holes for the purpose of this talk. The red points show the masses of the black holes that we have detected electromagnetically, so light. Whereas the blue points show the masses of the black holes that were detected to merge, that were seen through gravitational waves to merge in binary black hole systems. And I want you to note that the y-axis shows the mass of those. And I want you to note that this is in log scale. So it's immediately straightforward to notice that the black holes that we see electromagnetically kind of lay around this area up to 20 or so solar masses, whereas the black holes that we see in gravitational waves are, or tend to be much more massive. So looking at all of this already shows that there's a wide distribution of black holes that can be formed, and trying to understand that can become very challenging. And this brings me into the motivation to measure this, to do this work, to measure all those black hole spins. And I like to split this into two different categories. I measure one spin, and I measure a lot of them. First of all, as you may already know, black holes are really simple, and they're described by their mass and their angular momentum. So learning something about the spins of those black holes really tells us pretty much half of everything there is to know about those. But also looking at both masses, those stellar mass black holes and their spins, teaches us about how those black holes are formed and how they evolve. They teach us about the physics of the evolution of massive stars, the physics of supernovae, the physics of accretion disks, of X-ray binaries. It allows us to test general relativity. And I was running out of space on this slide, so I cut off the list. But then looking at why do we care about measuring a lot of them? Well, really looking at the whole distribution of black hole spins, of stellar mass black hole spins, it allows us to understand the whole stellar mass black hole population, and it enables us to relate the black holes that we see in X-ray binaries to the black holes that we see through gravitational waves. And this work will really represent the foundation for the next generation gravitational wave and electromagnetic, especially X-ray observatories. And lastly, and for my work, most importantly, it allows us to identify the biases and systematics that can go into our measurements when trying to think about those distributions. Now, to go into the techniques to measure this, the problem with looking at black holes is that they don't really emit that much light. So it turns out the best laboratories for trying to characterize those stellar mass black holes are represented by X-ray binaries. Those are binary systems in which a relatively normal star orbits a black hole. Now, this star usually sheds matter in one way or another, which forms an accretion disk around this black hole. We observe those systems in X-rays, and it turns out that in order to most clearly and definitively characterize the population of all the black hole spins, in order to probe the entire parameter space of both black hole and system, we need to look at a lot of those different systems. And as you can see, this gorgeous animation, though it's very downscaled, a lot of pixels I see. Anyway, this animation really shows a lot of the systems that were treated in my work. And this is to scale to give you a sense of the size of the accretion disk, to give you a sense of the size of the companion star, and it really shows how some systems can go from teeny tiny all the way to the great and impressive looking GRS 1915. How do we actually do this? How do we measure black hole spins? Now, the top three methods I listed here: discontinuum, fitting relativistic reflection or disk reflection, and quasi-periodic brightness oscillations or QPOs. Those have been methods that existed. They use X-ray spectra. They existed for as long as we've had X-ray spectra. The three in the bottom row here: polarization of X-ray emission, gravitational wave, or some features in the signals from gravitational waves, and actual direct observations of some supermassive black holes. Those are now becoming a possibility. However, as relativistic reflection is the main topic of my work, this is what I'll be talking about for the rest of this talk. In case you forgot from about 20 minutes ago in Riccardo's talk, I want to give a very quick reminder of how just naively this works. We have the optically thick, geometrically thin accretion disk around the black hole, emitting thermal radiation in the direction of our telescopes. Now, part of that radiation is upscattered by the hot electrons in this compact corona, which, as pointed out by Riccardo, we don't really know what's going on there. However, some of those upscattered photons propagate back in the direction of the disk, and they get reprocessed in the atmosphere of the accretion disk, and this is what we call reflected, the reflected emission. And all of those components together work to produce the observed spectra. So the blue from the disk, reflection, and the emission from that corona, all of them together produce this, this nice model shown here in black. However, for the purposes of measuring the black hole spin through relativistic reflection, we mostly care about this reflected component, about this green part over here. This figure over here on the right shows models for the expected emission, and the red curve shows the expected model in the rest frame of the black hole for some combination of parameters. However, due to the strong gravity in the proximity of the black hole, those features become smeared. They become blurred by relativistic effects, producing something that looks much more like this blue curve. And the spin of the black hole comes into play through the size of the innermost stable circular orbit, or the ISCO. As the black hole rotates faster in the same direction as the accretion disk, as the spin goes up to the maximum value of 1, that size of the ISCO shrinks, enabling the accretion disk to extend closer to the black hole. The matter that emits the X-ray radiation experiences more gravitational distortion, so the overall shape of the spectrum is more distorted. And by trying to characterize how distorted those emission features are, we can infer how close to the black hole the radiation is coming from, therefore probing the size of the ISCO, and therefore directly the spin of the black hole. Which brings me into my work. Now, I correctly anticipated that Riccardo will show a lot of spectra, so I'm not showing any spectra. And in here, I just leaped 5 years throughout all my PhD work, and I'm showing just the conclusion. And if you want to learn about what went into putting that together, go and look at the papers, or we can talk later. There's just a lot of analysis, a lot of spectra. I'm not showing any spectra today. I just want to show results and show cool things about those results. This plot is the grand finale of my PhD thesis, which comes with remeasuring or measuring for the first time, or remeasuring the spins of 36 black hole systems, about 11 of those for the first time, the rest up to 36. They're remeasured past measurements. The y-axis shows the magnitude of the dimensionless spin going from theoretically -1 to 1. The x-axis shows the names of the 36 sources. And the whole idea of my work was to develop a pipeline that enables us to really analyze all of those observations in a systematic way, using the same set of assumptions. I mentioned earlier to Julia that the idea is that if I'm wrong in the same way for all of them. So we don't have a bunch of authors making different assumptions leading to being wrong in different ways. Nevertheless, assuming that I'm right, we put together those measurements, those 36 measurements, and right off the bat, just by looking at the numbers, there's some cool things that you can infer. First of all, about 86% of those measurements allow spin values greater than 0.95, and 100% of those, all of the measurements allow within 1 sigma measurements greater than 0.7. Also, within 1 sigma, 28% of those 36 measurements definitively want to be greater than 0.9. So within 1 sigma, the error bar is entirely above 0.9. Now looking at the other end, 3% of those measurements allow values of spin less than 0. And if you're very quick at math, you're probably chuckling right now because 3% of 36 is 1. And even further, only about 17% of those measurements allow for spin values less than 1. So it's immediately clear that we seem to see fairly rapidly rotating black holes in X-ray binaries. But also doing this uniform work, doing this systematic work enables us to look at all those sources as a population, it allows us to compare apples to apples and put everything on the same scale. So in this figure up here, I show for the 36 sources indicated with different markers, I show from my work the spin measured versus the inclination. And this is exciting that for the first time we're able to do this on a distribution that we know is obtained in a systematic and uniform way. In terms of this, we see that this population of spins and inclinations, we see more overabundance around 60 degrees in inclination in those systems. This is expected given isotropic orientation of those systems. But we can look further and look at other parameters. We can look at, for example, the mass ratio between the black hole mass and the companion mass. And here we see an interesting trend. As the black hole mass to companion mass ratio increases, so for higher black hole masses, lower companion masses, the sizes of the uncertainties decreases. So not necessarily the value, but the size of the uncertainty decreases. And this is likely related to the efficiency with which the companion star overfills its Roche lobe and fuels the accretion onto the black hole. We can look at the inclinations that we measure from reflections, shown here on the y-axis, versus independent measurements of inclinations, such as from binary, the inclination of the binary orbit. And we can see here that while many of those systems follow the one-to-one trend, the diagonal line, some of them tend to have lower reflections inclinations when compared to the independent methods. Now, this might say something about how well the inner accretion disk is aligned with the orbit of the binary star. It might also say something about the magnitude of the natal kicks that black holes receive during the supernova that forms them. We can also look at, can I move this? Probably, if I know how to use this computer. Let's move it there because there's nothing in the plot there. We can look at the magnitude of the spin versus the black hole mass, and we can see similarly to, in the case of the mass ratio, we can see that the magnitude of the spins or the uncertainty of the spins decreases with increasing black hole mass. This is somewhat expected. The higher the black hole mass, the higher the accretion rate will be, producing more photons, just being overall more brighter, producing spectra that have higher signal to noise ratios, enabling better measurements. However, there's something very interesting that I want to point out here, with the exception of that one point, which is Cygnus X1, everyone's favorite black hole, or if not everyone, at least my favorite black hole. With the exception of Cygnus X1, all the other black hole systems that we see, or the black holes that we see in X-ray binaries, have masses less than 15 or so solar masses, which right away indicates that there might be something going on. We might be missing out on a lot of those systems. Looking, what's happening? There we go. Looking further, we can look at black hole spin versus distance, and here there's not much that's surprising. The uncertainties increase with distance, of course, lower flux. We have an overabundance of measurements around 8 kiloparsecs. That's around where the center of the galaxy is. And then we have some outliers over here on the right. Those are the extragalactic sources, LMCX1 and LMCX3. Those are just bright and famous and lovely. Anyway, we can look at black hole spin versus the mass of the stellar companion. And something that's very interesting to note here is that, again, with the exception of two systems, the high mass X-ray binaries, many of those systems have companion masses less than 2, 3 solar masses, which really begs the question, how do you form a binary system in which one of the stars is so massive, 50, 40, 60 solar masses, that it can die and produce a 10 or 20 solar mass black hole, with a companion that has a 1 or 2 solar mass star, and have that star survive things like common envelope, evolution, just overall throughout the age of this? How can that happen? How can you form systems with such high mass ratios, and how can they survive something like that? And lastly, we can look at something like the black hole spin versus the orbital period of the binary in days. And the curves that you see here represent theoretical predictions for the upper limit of the spin that a black hole can have if the rotation is entirely acquired just through accretion. And that's for different black hole masses, 5, 7, and 9 solar masses. And most interestingly, you see those points up here, which are abnormally high when compared to the theoretical predictions, which indicates that the spin in those black holes could not have been entirely acquired by accretion, which means that at least some of those black holes must have formed already rapidly rotating. So putting those measurements together, we can draw the distribution of black hole spins in X-ray binaries. This figure here shows, in red, it shows the distribution of black hole spins pre-merger from the 3rd edition of the Gravitational Wave Transient Catalog. That's this red curve over here. And the blue distribution that I show here is entirely based on the measurements within my 36 samples. Now, it's very important to note, this is an observed distribution. This is not necessarily the intrinsic distribution of black hole spins in X-ray binaries, but you can see immediately that those distributions do not agree. They're in clear disagreement. And this can point at different formation channels for the black holes that we see in X-ray binaries, the black hole that we see to merge through gravitational waves. And it can indicate that those systems have different properties of the binary orbit, different properties of the progenitor star, and so on. It just might indicate that those are different black holes. And with that, I want to just spend the last couple minutes talking about what the future of this looks like. Now, when looking at this distribution, no, didn't want to spoil the punchline. When looking at this distribution, there are two things that immediately come to mind, and those are the two very things that I'm working on right now. First of all, are there any measurement biases? Anything in our analysis that leads to us measuring artificially high black hole spins? Now, the figure on the right here shows within our spectral fits for the 250 observations of those 36 black hole systems. Within all of those, the spin on the x-axis versus other parameters within the spectral fits on the y-axis. And this enables us to really look into whether there are any correlations with parameters, either with just spin or between other parameters themselves, that could lead to artificially biasing our spin in one direction or the other. And as it turns out, based on the preliminary analysis that I have so far, there is one trend that could be biasing the spin, but it's biasing it in the wrong direction. And that's up here where especially for low quality spectra, the spin of the black hole tends to be biased towards low values. So that's exciting. It kind of indicates that we can trust those measurements. However, looking at the figure on the left here, this shows for the same sources on the y-axis shows the spin measurements from my work through relativistic reflection versus archival measurements of the spins of the same black holes obtained through continuum fitting. This is one of the other 6 methods that I highlighted in the beginning. And you can see that while some of those sources follow the 1-to-1 trend, there's some out there that do not. And this, I've been calling this plot the good, the bad, and the ugly plot, because you have the good here, you have the bad there, and then you have the ugly over here, because there's nothing that is reliably measured to have low spins through both methods. So just trying to think about what's happening with those, with this discrepancy between continuum fitting measurements and relativistic reflection measurements. This is a very interesting issue. I'm currently working with an undergraduate student at MIT trying to really answer this question and trying to statistically reliably think about what goes into those measurements. So that was the first thing that jumped at me when seeing that distribution. The second thing was, are there any detection biases? So let's ignore the mess on the right, and I want to focus on the thing on the left for now. That figure shows on the y-axis the flux for some simulated X-ray binary systems for different spins, for different black hole masses indicated by the different colors, at the same distance, at the same mass accretion rate, at the same inclination, at the same everything else is held the same. And you can see that for increasing spin, the flux goes up. That's not all that surprising. However, what is surprising is that this horizontal black line, that shows the detectability threshold of an instrument such as MAXI, the All Sky Monitoring Survey, X-ray, somewhere in there in the acronym. And what's immediately striking here is that we miss out on a lot, especially a lot of the low spins. First of all, we miss out on a lot of the more massive black holes. So you can see that, for example, for the 20 solar mass black holes, we only see them if they're very rapidly rotating in this particular configuration. So this kind of indicates that there might be a bias against the more massive black holes, and there might be a bias against lower spins in terms of just observation in terms of flux. So what I did was I simulated, I think 100,000 or a million, I don't remember how many zeros I put in there, X-ray binary systems with, and that's shown here in the blue histograms, with uniform distribution in spin, some variability there, uniform in inclination, some distribution of companion masses that just resembles some IMF. The mass distribution for the black holes that is informed by the LIGO distribution of masses seen in black holes and stellar mass black holes. And then a distance distribution shown here in blue, just things scattered throughout the galaxy. And based on that, based on physics that I took from white dwarf binaries, from cataclysmic variables, where I was able to link their accretion rate to the mass of the companion star in a linear way, I translated the same physics to black holes, assuming that the accretor is agnostic of what the matter is being accreted on. So by doing that, I generated this flux distribution, and then I placed the same cutoff, this black line over here. And what's left on the right are the red measurements, what we can see above that detectability threshold. And now this enables us to go back and look at the figures. We see that the distance distribution is not all that interesting. For the black hole mass distribution, we're really missing out on the high mass black holes. On the companion mass, we're missing out on the low stars. They don't shed that much matter. The inclination distribution is not all that interesting, but the spin distribution does show that trend of preferentially detecting rapidly rotating black holes. So this is still preliminary work. This is something that I'm very excited about doing in the next few years. And I hope that I convinced you that this is cool, this is interesting, and there's a lot more that we don't know about yet. And with that, I want to thank you for your attention, and I'll take some questions.
Any questions for Paul?
Thanks, and it's good that you try to do everything with the same model to see how things work. And now you also show, so among the things you do, you show comparisons to mass of the black hole, distance, mass of the companion. Those are not coming from your analysis. How much do you trust those measurements? And they are not coming from the same method, all of them either. So I'm wondering whether you are being biased or for good or for bad, right?
I'm trying to be pragmatic here in my answer and just say that I trust them as much as I trust anything else that I read. You know, taken with the grain of salt, this is the result of other people's work, which may or may not be right, but similarly, my work may or may not be right. So, you know, it's true, it's very true that those come from different methods. They, you know, the distance measurements, the mass measurements for the black holes, the mass measurements for the companion, star mass for the orbital inclination.
The reason why I ask is because some of them are dynamical, so
Yes.
we can trust them more, you know. But some of them, I guess, are coming also from spectral analysis that use a different model than the one that you are using.
I see. I did not include those. When I said independent measurements of mass, distance, and so forth, I made sure those measurements do not come from X-ray spectra. So they're all dynamically confirmed. How much I trust those? Well,
Expect you meant this implicitly, but I'd just like to check on your flux versus spin as with various masses. If you keep, that lovely picture there, which explains a lot. You obviously, if you go to even bigger masses like the gravitational wave masses, they become even harder to see, and that's what you intended, I see.
yes. Yes, that's exactly what I was intending. And, you know, just naively, to get a sense of why that is happening, well, we see those spectra in X-rays, and as we saw in Riccardo's talk, we have a lot of contribution in UV. As you move to higher masses, your accretion disk shifts to lower energy, so it kind of just shifts out of the observable band of max. It just shifts out of what you can see.
The question I have is on the distribution of companion masses. Is that what you're showing in the upper left block?
Oh, in here,
Yes.
this thing over here.
And the blue versus red is what again?
Sorry, the blue is the assumed distribution what I generated those 100,000 or a million systems with. It might have been more intuitive if I plotted those two in log scale to show that this actually resembles an IMF. But since I didn't have the foresight to do that, you'll have to trust me that this does resemble just an IMF.
So this is dominated by black hole LMX speeds, right?
Yes.
We only have 3 or 4 HMX speeds. The LMX speeds, it's always been a very striking result, which I'm sure you're aware of, is for the spectroscopic mass of the companion. They're dominated by K dwarfs. That's only 0.5 solar masses. It's a great puzzle. I think I have a model that they're long overdue in putting together and writing up, but that's a big question mark in this whole evolution story.
So you're absolutely right. And I had this slide initially in the talk, and then I took it out because I realized it would take me way too long to talk about this. And even though it's extremely interesting, and the title that I put there is when do those X-ray binaries exist? What I did in this figure on the right is on top of an HR diagram, I took all the systems for which we know the orbital period in days. And I did something that I want you to follow me and try to really pay attention to what I'm doing and see the irony in it. I assume that those are main sequence companion stars. If they're main sequence companion stars at this orbital period, I know that they're Roche lobe overflowing. I can calculate their density. Then by taking their density, and again assuming that those are main sequence stars, I can calculate their expected luminosity from what we know about stars. But also we have the color index for the stars, I can determine their temperature. So what I did was by repeatedly assuming that those are main sequence stars, I calculated their luminosities and temperatures, and then I put them back on the HR diagram. Now, I repeatedly assumed that those are main sequence stars, so they better land back on the main sequence, if they are. And as you can see, many of those do not. They really do not land back on the main sequence, really indicating that a lot of those systems have evolved companions. And it might mean that in order to produce an observable X-ray binary to have enough emission, you need something that is wide enough to survive something like a supernova, but is also evolved enough so that the companion star evolves off the main sequence so that it can fill up its Roche flow and start fueling accretion onto the black hole, but that is a fairly short-lived period. So that's why I named this "When do X-ray binaries exist?" Because if you look at some simulations of X-ray binaries, so this is for some metallicity, this is simulated work from a group in New Zealand for black hole masses between 5 and 40 solar masses, Roche lobe overflow accretion periods between 1 and 30 days. Again, this is an HR diagram. Main sequence over here, you can see that the colors that indicate that there exists sufficient accretion to be observed, they all happen after the companion star evolves off of the main sequence so that it can get to puffing up and overfilling its Roche flow. So this is extremely interesting, and it's an extremely important question to ask. How do those systems form and how do they evolve? How do they survive? And something that's even more interesting and people don't really take into account is what is the fraction of triple systems in those systems, in those multiple stellar systems that have a black hole and other companion stars, because it might be that a black hole will form and then interactions between the two less massive companions in the triple system just shoots one of them inside to an orbit where it can then become an X-ray binary. So those are all open questions, and that's why I gave this talk, just showing open-ended things, because I wanted to have a discussion and talk about cool things.
So I'm afraid we should finish up here, but let's thank Paul and Riccardo. So if anyone read my email apart from Jenny, please head to the head lounge when we'll be having some coffee and tea with our speakers. And this is an initiative that Antonella suggested. So thank you very much for arranging it and suggesting it. Okay, see you next week.